Okay, so let's start. Basically, we finished the topic of inlets, so this is done. We talked about subsonic, supersonic inlets and the flow characteristics inside those inlets. And now, today, we will talk about exhaust nozzles, okay? Which we actually, the fundamentals of which we actually covered, if you remember, in aerodynamics 2, especially the convergent divergent nozzle related flow physics. We discussed this. But in terms of propulsion system, let's draw a typical convergent divergent nozzle here. Okay. By the way, nozzles can be either like that, so converging, diverging, or in some propulsion systems, we also use only converging nozzle as well. Only converging, okay? So of course, the thing is, any nozzle, I mean, here we are, in this class, we talk about nozzles in the context of turbo engines, okay? Turbojets, turbofans, and everything. But of course, other types of propulsion systems, they do have similar type of nozzles as well. For example, rocket engines, liquid or solid fuel rockets, they do have nozzles, and almost exclusively they have converging, diverging nozzles. There's a reason for this. But in any case, nozzle, whether it's used in a turbo kind of engine or it's used in a rocket engine, it has only one purpose in life, only one mission. Its mission is to receive or convert the high energy fluid or high enthalpy fluid that it receives from some source. In turbo engines, that source is that high enthalpy is generated in the combustion chamber. Some of it is reduced during at the turbine, but still after the turbine, it's quite reasonably high enthalpy level. In a rocket engine, there is no turbine, so the nozzle is directly attached to the exit of the combustion chamber. So therefore, nozzles receive high enthalpy fluid, and it has one mission in life. That mission is to convert that high enthalpy into high kinetic energy. Okay, so because especially like turbojet engines and similarly rocket engines are entirely depend on generating high U exit or high exit kinetic energy. If you remember, we discussed this. So this is the only objective of a nozzle, whether it's converging, diverging, or diverging. There is one big difference. Converging, I'm sorry, only converging nozzles like the one here, their performance is quite limited. Okay, performance meaning that the U exit levels are quite limited. Why do you think this? The reason?
It have to be subsonic.
Because they are.
Yes.
Because they are choking at Mach 1.
Can you repeat again?
Because converging nozzles only can reach the Mach 1 at the exit.
That's right. Exactly. They can only reach Mach 1 at the exit. Because that's the minimum area location. The flow, I mean, maximum mass flow rate, if you force this nozzle to operate at maximum mass flow rate, Mach number will be equal to 1 here. It cannot go to supersonic. But here, converging, diverging, that's not the case. It can be very high supersonic at the exit. Okay, so for low performance aircraft, maybe subsonic flying, but turbojet engine aircraft, we can still have only single converging nozzle that works. But if we need high performance aircraft or rocket engines for sure, we need supersonic exit Mach numbers, therefore very high velocities. So therefore we need to have converging, diverging nozzles. So therefore, the objective is to convert let's say, let me reword it. Generate as high kinetic energy at the exit as possible. So this is the this is its objective, but there's something that we need to be careful about while doing this, trying to achieve this objective, let's say, with minimum PT loss, with minimum pressure loss. This is a non-rotating component. It's in reality a simple duct flow, yes, but we can lose total pressure. How can we lose total pressure here?
Surface friction.
We have two mechanisms. Surface friction, meaning viscous losses, meaning boundary layers will always be there on the walls. So they will contribute to total pressure loss. And there is one other possibility.
Expansion?
No. Shock waves, right? Normally, I don't know if you remember from aerodynamics 2, under design condition, design operation, there is no shock waves in the nozzle. There are no shock waves, I mean. Shock waves while we are starting the nozzle, meaning if you remember, we discussed things like this. For example, this is, let's say, we have a P exit, yes, and we start from subsonic flow. This is the case for rockets. Also, this is the case for turbo engines. Subsonic flow is incoming. We choke it, yes, M equal to 1, and then we go to supersonic if it's converging, diverging. Now P, and then we said, okay, let's start from everywhere subsonic, and then let's keep reducing PE step by step. And we keep reducing it, we reduced it, we reduced it. Every time we reduced it, the flow started to accelerate inside. But at some point, during that process, sometimes we ended up with shock waves in the divergent part, if you remember. As we kept lowering PE, this shock wave, normal shock wave, moved to the right. And at a certain PE, it actually went out of the nozzle. At that case, at that specific PE case, we have fully supersonic flow in the diverging part and no shock waves. That's the best condition because we don't have shock waves and we don't lose any total pressure. Okay, that's the design condition. That was not the case for intake, if you remember. In a the intake that we discussed, the pitot type intake we discussed on Tuesday, it does have a converging diverging geometry, yes. But we do need a normal shock wave in that inlet. We cannot live without a shock wave because that shock wave is the only mechanism to reduce to subsonic speeds. That's at the intake, we need low subsonic in the compressor. So that shock wave has to stay there. But in the nozzle, there shouldn't be any shock waves under design operation. Do you understand this point? So, and how do we ensure that there are no shock waves? PE must be at a certain level, PE. And that corresponds to a certain pressure ratio, PE over P0 and everything that can be calculated. That's related also to the geometry and everything. Those are some fundamentals we discussed in aerodynamics too. But also there is one important issue regarding here nozzles. This PE, I mean, the relationship of PE with respect to the atmospheric pressure outside. Yes, sometimes P0, PA, or sometimes we call it back pressure, PB, back. Okay. And the ideal case is when PE actually is equal to P back or P0 or P atmosphere. And if it's not equal to that, we may have different operational modes of the nozzle. We discussed this, we will remember it also today. But for example, what is the relation between PE and P back or P atmosphere for subsonic flight?
They're equal.
They are always equal. Why are they always equal? What is the physical mechanism that keeps them equal all the time? If the exit velocity UE is subsonic or ME is subsonic.
Because there's no shock wave.
Yeah, there's no shock wave, but there is a physical mechanism. Somehow, exit knows what the back pressure is all the time. So it always keeps it equal to back pressure. How does it know that?
Because there is no choking.
Huh?
There's no choking of the throat if it's entirely
No,
subsonic.
I'm talking about back pressure. Choking is upstream.
But once it gets choked, then it has no information about what's happening at the back.
So if it's subsonic,
Mm-hmm.
the back pressure information is propagated with speed of sound. That speed of sound waves reach the nozzle. They can reach because nozzle is exiting at subsonic speeds. Information is oncoming at sonic speed. So nozzle always knows what the back pressure is. So it also always keeps equal. However, when the jet becomes supersonic, nozzle does not know what the back pressure is. It has its own PE. And it may be bigger, it may be smaller than back pressure. Why doesn't it know what the back pressure is? Because that information, which is propagated by sound speed of sound, cannot reach the nozzle because nozzle is issuing faster than the speed of sound. We understand this point. Bence çok anlamadınız bunu. This nozzle exit is going with faster than the speed of sound if it's supersonic, yes. The back pressure information is propagating here with m equal to 1. This wave cannot reach here. Cannot reach here. So this does not know what the back pressure is. So it becomes independent of back pressure. So this means that it can be bigger or smaller than back pressure, which kind of resulted in different operational modes we discussed, if you remember, and I will draw it again. This under-expanded nozzle, over-expanded nozzle, things like that. That's for supersonic exit nozzle speed. Yes, nozzle Mach number. If it's subsonic, there's no such thing as over or under-expanded. It's irrelevant because it's always equal. Yes, we discussed this. Anyway, I will come back to this point in a second. And but we try to match PE and P0 as close as possible for maximum thrust generation. Okay. And how do we, in high performance aircraft, how do we ensure that this is the case? Most of the time we use variable area nozzles. Okay, so we this cross section, let's call it AE. We use what we call variable area nozzles. So the flight control system actually, or sometimes engine controller actually, can manipulate this exit area. Sometimes it can make it smaller, sometimes it can make it bigger. As this exit area to throat area ratio is a function of Mach number. So if Mach number is equal to 1, this becomes equal to A star, things like that. So AE to A star ratio is a function of Mach number. By playing with AE, it can regulate exit Mach number, and therefore it can regulate exit pressure. Flight control system. Flight control system is a smart system, guys. Okay, it knows all the equations that you know. Okay, that computer knows everything that we taught in aerodynamics too, all the equations. So it can do those calculations and actually change the exit area. There's one reason, another requirement that we need area change. So in some engines, in nozzles actually, we use afterburners. Okay. When we use afterburners, that of course changes the enthalpy level of the fluid, therefore increases in reality the total enthalpy or H0 stagnation enthalpy level of the fluid. So therefore nozzle can accelerate to higher and higher Mach numbers, especially if it's convergent divergent. Then in that case, we also need variable area. In some engines, the engine not only controls the exit area, but also the throat area as well. Okay, it has some mechanical means, some hydraulic system to change both the throat area and the exit area. It can change it. So for afterburners and for this purpose, matching as much as possible PE to P0, especially at supersonic jet exit conditions, we need this variable area nozzles. In addition to area variation, in some nozzles in modern aircraft, we also have what we call thrust vectoring. Okay, the nozzle can actually change the direction of the velocity vector, not only its magnitude. The variable area nozzle changes only its magnitude. It can change only its magnitude. Thrust vectoring also changes the direction of the vector. In some aircraft, like F-22, for example, it has two-dimensional thrust vectoring. So the thrust vector is changed only in this axis and this axis, in two angles only. In F-35 and in some SCOI aircraft, it can change at any angle, 360 degrees. It can rotate the nozzle to any angle. Okay, of course that helps, especially for fighter aircraft, if they want to do some strange or crazy maneuvers. Of course that helps, because during those strange, crazy maneuvers, wings will stall actually. So there will be no lift generation on the wings. There will be no airflow around the wings. At those instances, thrust vectoring provides the lift as well. Okay. Yeah. Normally we don't do that. In conventional aircraft, thrust is used only to overcome drag. It has nothing to do with lift, right? Normally, under cruise condition, thrust must be equal to drag. T must be equal to D. So the drag is actually normally much lower force compared to lift, much smaller compared to lift. So thrust is not very high during cruise flight. It just has to be equal to the amount of drag, so that in that flight direction you can maintain constant velocity, no acceleration flight, because net force is zero. Thrust is equal to drag. But that's the case for passenger aircraft. That's the case for cruise flight, for fighter aircraft. But for maneuvering, strange maneuvering cases, dogfights and whatever, then lift can be lost totally. If you have thrust vectoring capability, you don't crash to the ground. It's already coded into the flight control system, and the aircraft takes care of that. And what else? Another issue with exhaust nozzles is that so we need variable area nozzles. Let's also keep it here as a note, thrust vectoring. But sometimes we also need, as you might know, thrust reversing. Okay. We use this regularly in all passenger aircraft as well. So during landing, for braking the aircraft, quick braking of the aircraft, we put some panels at the back and divert the jet towards front, so that momentum change, the almost 120-degree direction change of the jet vector will slow the aircraft down, because it will create a reverse thrust now. Okay. So that's another That's another system, let's say, integrated generally into the nozzle design. And what else? One issue is that the temperature of the gas exiting the nozzles is quite high. I mean, the highest temperature in a turbojet engine is not at the nozzle, it's at the combustion chamber, at exit of the combustion chamber and inlet of the turbine. That's the highest temperature location. Turbine extracts some energy of the fluid, so the temperature drops down a little bit. Both the total and the static temperature drops down. So when it reaches the exhaust nozzle, temperature is already lower than the combustor exit temperature. However, still warm enough, still hot. So generally exhaust nozzles have to be cooled. But if it's a rocket engine, there is no turbine. So the exit of the combustor is directly forced into the nozzle, in converging diverging nozzle. So gas temperatures are extremely hot in a rocket engine. Plus, in liquid fuel rockets, for example, I mean, in turbo engines, we use, for example, hydrocarbon fuel. But in liquid fuel rockets, we use hydrogen as fuel. The heating value of hydrogen is almost maybe more than 2 times higher than hydrocarbon fuels. Okay, so the heat release because of that exothermic reaction of burning of hydrogen is very, very high. So this means that gas is extremely hot and you really need to cool down the walls of your liquid fuel rocket nozzle exhaust. How do you cool them? Any ideas? Divert the air of the rocket. You can do that. It's nowhere going to be enough. Diverting air from outside to cool it, it's not going to be enough. It will not save you. Your nozzle will melt. We do something else. Any ideas from online participants?
Opening air channels into the nozzle.
What?
Opening air channels to the nozzle.
No, that's not going to be enough.
Propellant pass through the nozzle, maybe.
Bir daha söyle.
Fluid flow around the nozzle, maybe inside.
Anlayamadım.
Fluid flow around the nozzle, maybe
Fluid flow around the nozzle. What kind of
Yeah.
fluid?
inside. Maybe the propellant or
Propellant, yes. So we cool the nozzle with fuel. Okay. What do I mean by that? So I mean, fuel is liquid, in liquid phase, hydrogen and oxygen, yes? So they are very cold, actually. To keep them in liquid phase, they are what we call cryogenic. So they are kept under cryogenic fuel tanks. The fuel tank of the liquid fuel engines are cryogenic, so they are very cold. And then we basically wrap around the nozzle a lot of piping, spiral piping, and basically pump liquid fuel around the nozzle, outside, attached to the walls. That cools down the nozzle walls. That's nice. We need cooling of the nozzle walls. Plus, that raises the temperature of the fuel a little bit. That's also nice because it helps me to spend less pumping energy when I'm trying to inject into the combustion chamber. So it's win-win situation. That's how we cool the walls of rocket engines. If you check the Raptor engines for SpaceX, it's like that. If you change the engines for Apollo, it's like that. It's just generally a well-established technique. Okay, but for turbo engines, the temperature is high, but not that high. So some kind of air cooling will be enough. Okay, some kind of air cooling will be enough. You don't have to wrap around fuel lines. You may need to in some situations that can be done, but air cooling also may work. Another issue is that nozzle has one purpose, to generate high kinetic energy at the exit, but high U exit is also means it also means high noise. Okay. the acoustic signature of this engine and the noise generation is proportional to UE to the power 6 or sometimes 7. Okay, so that's why rocket engines and turbojet engines are extremely noisy, because UE is very high. Yeah, also the infrared signature issues are all related to nozzle design. Sometimes, sorry, the exit temperature is of importance. If you remember, we talked about mixed flow turbofan engines. Mixed flow turbofan engines, while they generate reasonably high U exit, they also drop down the temperature a little bit because they mix cold and hot flow before they eject into the atmosphere. So reduce the temperature, so the infrared signature is reduced. Let's remember the topic that we discussed a few minutes ago regarding the operation of the convergent divergent nozzle. So when we have this jet going out, at the exit plane we have a PE and we have a P0 or PA outside. Okay, when let's say and it's supersonic exit, so M is greater than 1, M exit is greater than 1, M here is subsonic, and let's say it is choked here. In this case, if PE, P exit is less than P0, what did we call it? Do you remember?
Under expansion?
Over.
Under or over?
Over.
Over.
Overexpanded.
Overexpanded. Okay, the thing is, if PE is, normally what do we want? We want PE equal to P0, yes? If PE is less than P0, it means it's expanded more than we needed. PE dropped so low, it's lower than P0, it expanded much more than we needed. Abarttı yani. Overexpanded. Okay? That's why we call it overexpanded. Gerek yok bu kadar expanded. P0'ya kadar expanded. So if that's why we call it overexpanded. So PE less than P0. Bunu onun için ezberlemenize gerek yok. Yani bu tip anekdotlarla hatırlayabilirsiniz. Overexpanded, yes. When we have an overexpanded nozzle, so PE is right here, the static pressure is lower than the pressure right here. What kind of flow pattern do we have outside of the nozzle, just outside of the nozzle?
Oblique shock waves?
Yes, why? Because a jet is at low pressure, but suddenly it encounters a high pressure environment. It's like it basically hits a wall, okay? And then suddenly encounters this high pressure means that it will generate some kind of oblique shock waves. And these are also, it generates what we call diamond shock patterns at the exit. Okay, so this is the overexpansion case. So this is marked with red. Now I'm going to use a different color for the other one. The other case, PE greater than P0. Okay. Yes, we call it underexpanded, but we call it underexpanded for a reason. Okay, the reason is that normally, yes, we want PE at the level of P0, but it's not. It's higher than P0. So it's not expanded enough. It has to expand more. Yes, it's not expanded enough. We call it, therefore, it's underexpanded. It's not expanded enough. That's what we mean by underexpansion. And then when we have underexpansion, and I'm going to use the green color for this, when we have underexpansion, now PE is higher than outside. Okay, so instead of having oblique shock waves, it will suddenly encounter a lower pressure environment. It has to quickly expand, very quickly expand to the atmospheric pressure. That happens through expansion waves. So in that case, we end up with these expansion waves instead of shock waves. Okay. So, but both of them are inefficient operation. And why do I say inefficient operation? Because of this. Because we use generally this parameter to indicate the performance of a nozzle. We call it gross thrust coefficient. Gross thrust coefficient, CFG we call it. And it's defined as m dot, mass flow rate going through the nozzle, times U exit, and plus PE minus P0 times A exit, divided by m dot times U exit in the ideal case. When I plot the variation of CFG, with respect to P total exit over PE, P total exit over P exit is a function of exit Mach number, basically. So I'm plotting with respect to exit Mach number. You can think of it also like that. It looks something like this. It reaches a maximum at this point. CFG, the gross thrust coefficient, reaches a maximum, and this point is where you have PE is equal to P0. To the left of this, this is under expansion, and to the right of this, we have over expansion. This axis is not PE, don't get confused. This axis is kind of 1 over PE, because PT, how does PT change through the nozzle? What is, can you plot the PT variation? Let's say this is x-axis, x PT variation along x for a nozzle.
If it's an real actual nozzle, it will get lower.
So if it's an actual nozzle, it will drop like that. That's what you're saying.
Yes.
If it's an ideal nozzle,
it will not change.
It will not change. Yes, it will stay constant. So what causes this drop?
Losses from the walls.
So viscous losses on the walls. Boundary layers, that is. What else?
Shock waves.
Shock waves. If we have one, I mean, if we have any. So otherwise, I mean, boundary, in reality, of course, boundary layers are always there. But one thing that we need to be careful about, I forgot to tell you, is that let's say we started the nozzle, we reached to its operating design condition, so there are no shock waves. However, there will be boundary layers, but one thing that we need to be careful about is the fact that the flow potentially can separate in the diverging section from here, from these walls. If this sudden this geometry changes, let's say, happening very quickly, you may end up with flow separation near the walls. That will, of course, add up to big viscous loss. You don't want that. But in any case, generally, of course, when we are designing, we try to be careful enough. When we are manufacturing the nozzle, our tolerances will not be very high, especially if we are designing a supersonic nozzle. Our manufacturing tolerances will be very low, because any variation, for example, in the walls, we don't want any steps or anything like this in this geometry variation. First of all, if you have steps, significant amount of steps, it can trigger local separation. We don't want that. Plus, it will trigger expansion and local expansion or shock waves, which can interact with something else. We don't also want that. Okay, so manufacturing is critical, but in any case, PT is constant. Let's say, or close to constant, drops a little bit. But so therefore, this axis PT over PE, no, this does not change much. This changes a lot. So that's why I said this is similar to plotting 1 over PE. So that's why this axis is not PE. That's why we have under expansion to the left. If this axis were, if it was PE, on this side we have PE less than P0. So this actually should have been over expansion, right? But it's not, because this is kind of 1 over PE. Don't get confused. So this is like an actual nozzle. In an ideal nozzle, even at PE is equal to P0, we would have gotten a much higher CFG. And the reason between this difference, I mean, the reason of this difference is, yes, we know the viscous effects, but there's also one more effect we call flow angularity at the exit. Okay. Flow angularity means that normally we would like to have a nice and straight jet going out, right? Because our thrust, I mean, why are we generating a jet in the first place? Our objective is to generate thrust. The thrust vector is aligned with the shaft axis of the engine. It tries to push the engine forward, yes? Now, therefore, jet is the one that is creating this thrust. So therefore, the U vector must be aligned with the thrust vector. I mean, putting aside all the thrust vectoring discussions. So this jet vector must be aligned with the thrust. Is it really like that in real life? Meaning, is the angle perfectly zero, mathematical zero? Not. Because of 1,000 different reasons, the jet vector will be misaligned a little bit, okay? It may be up or down a few degrees, left or right few degrees, it will be misaligned a little bit. Every misalignment will cause you thrust reduction. Okay, so that is what I mean by flow angularity in actual cases. And if you have some kind of under or over expanded nozzle, you will definitely have flow angularity and significant amount of flow angularity. That's the major source of thrust reduction. We can basically, for some propulsion systems, we can manage this flow angularity by playing with the nozzle, either vectoring it or with changing the area. But for some propulsion systems, we don't do anything. For example, for space flight, rocket engine nozzles, they do have thrust vectoring capability. In fact, this is how SpaceX can land all those systems back on Earth by thrust vectoring. However, when flying up, it takes about 8 minutes. In 8 minutes, from sea level to space, okay? Sea level is almost 100,000 Pascal pressure outside P0, space 0 Pascal pressure. So in 8 minutes, it travels through, in the sea level condition of jet exit is always supersonic in the rocket engines. So at the sea level, atmospheric pressure is very high compared to P exit. So you see basically over expansion at the sea level. So just at the launch pad, if you look at the nozzle, you see all these diamond shock patterns. So as it moves up, it reaches to a certain location where P is equal to P0 and then passes that. And then when it reaches near, very high altitudes in the atmosphere and in space, the P exit is higher than P0. In space, P0 is actually 0, so it's always higher. So you see very much under expanded jet, very wide jet exiting the rocket engine nozzle. So if you watch few launch videos of any rocket system, old space shuttle videos or SpaceX videos, you can see You can see that under and over expansion. We don't do anything about it because it's only 8-minute flight. Okay, it's not like sustained hour-long flight. But for sustained flight, like the nozzle of a fighter aircraft, we have to do something. I mean, we cannot let it be by itself. Whatever over or under expanded, we can just let it to itself. So we manipulate with the area or something like that. Try to match PE is equal to P0. So keep the CFG at its optimum operating condition, maximum CFG condition as much as we can all the time. Okay. Any questions? Online questions or face-to-face? No questions? Okay, then. So let's stop here and let's meet again on Tuesday.
İyi günler hocam.
İyi günler.
İyi günler hocam, dikkat edin kendinize.
İyi günler.